Hello and welcome back to Calculus 1 section 5.4, working with integrals. Funny title, right? So we're going to put everything we learned together so far and introduce few new formulas. Some of these formulas are quality of life formulas, and some formulas will be important for calculations. So let's see what we have. I'm going to go all the way back first and make sure that everyone is on the same page with integration. So we started with integration in 4.9, and we said that integration is going to undo derivatives. So I started by d dx of x squared 2x. Integral of 2x dx was x squared, and then we said you have to use the plus c. So if you have any type of exponent, even if you have, let's say, integral of, I don't know, cube root of x dx, you will rewrite that as integral of x to the 1/3 dx, and then you will add 1, so x to the 4/3 divided by 4/3. You can put 3 on top, right, to save a step and do this. So these guys were known as indefinite integrals. Integral of sine x dx is negative cosine x plus c. So all of these were known as indefinite integrals, and you would always put plus c at the end because it gives the family of these functions, and if you have initial condition you can calculate the value for c. And then we moved to the idea that you can use integration to calculate area under the curve. So if all of the function, right, is above x-axis, in that case we can find the area by solving the definite integral, and this definite integral is integral a to b of f of x dx, and we solve it by figuring out any of the antiderivatives first, and then say f of b minus f of a. This was also in the fundamental theorem of calculus. So if we had to calculate the integral of, let's say, x cubed, let's go with x squared, minus 1 dx from, let's say, 2 to 5, you would have x cubed over 3 minus x computed from 2 to 5. So we first find the antiderivative, and then we compute from 2 to 5. So that's going to be 125 over 3 minus 5 minus 8 over 3, and then plus 2, because minus and minus gives you plus. Maybe I should, you know what, let me do this way. So now I have 125 over 3 minus 5, I'll put 15 over 3 minus 8 over 3, and then plus 6 over 3. I just want them all over 3 so we can deal with that. 125 minus 15 is 110, and then minus another 2, so that's 110 minus 2 is 108. So 108 over 3, now 1 plus 8 is 9, so that's divisible. It goes 36 times. So the answer is 36 for this problem. The area under the curve would be 36. So we have indefinite integral, which we studied in 4.9. You get the function at the end and you put plus c. Then in 5.2 we did the definite integral, which gave us the area under the curve. Now let me just box this in. Now we move to some of those formulas which we had before for definite integrals. First one would be, if you are integrating from a to a, f of x dx, you will get 0. That should make sense from multiple angles. First off, think about the solution of this. You would find some antiderivative, and then when you plug in the limits, you get f of a minus f of a, and that must be 0. I mean, that's the quick proof. But there's faster proof than that. If you just reason of what this thing does. Our integrals are, right, the definite integrals are computing the area under the curve. So we know that it goes from A to B. But if it goes from A to A, then the width is 0. When you multiply height by 0, you get 0. So area must be 0 because there is no width to this. All you have is a function, right? And then you have one point, A. And the other A is at the same location. So when you're looking at this rectangle here, it has 0 width. And if it has 0 width, then it has 0 area. Another cool thing that we might use very soon is swapping the limits on the integral. So this is integral, instead of a to b, now b to a, f of x dx, and if you want to put equal in between, you have to put a negative sign there. So in some cases, when you do substitution, which is the next section, you might end up with the integral that looks like this. And then you have stuff over here. So now you're looking at this and say, well, the lower limit should be the smaller number. So what you do is you put the smaller number down, put the larger number on top, and put this minus sign. Again, proof for this is very easy. You compute the f of x, over here you have from a to b. Over here you compute f of x, but you get negative f of x, and you get b to a. So now when you write these out, this minus obviously will propagate and change the sign so it will look the same for both sides. So that's just a quick outline there. And then the one that we already covered, a to b f of x dx, this is the one where you can interrupt your interval for integration with any number, and then just keep adding all of these together. So I can say a to b could be integral a to c f of x dx plus integral c to b f of x dx. You can interrupt as many times as you want. So what this means is that if I have integral a to b, I can pick a value c, and you can see that once this area here is calculated from a to c, and the other area on the other side is calculated from c to b, when you add them together, you get the overall area between a and b. So you are allowed, at your convenience, to break the interval anywhere you want, and with a value c. And we've already seen that this is very useful, because once we get those negative areas, right, we can break our integration at every point where it dips below, where the function dips below x-axis, and isolate that part, put the absolute value on it, and move on. So these are the formulas that we covered before. This is, yes?
Well, chapter 5.5.
Yes, in its full might. Dare I say more than others. So you're allowed to interrupt your interval at any point between a and b, and then just add. Now, how many times can you interrupt? As many as you want. As many as you want. So what do we do? The next one is, what else is there? I don't think there is anything else. So that's the review of the old stuff. Now we're going to take a look at the new stuff. And what we have first is the quality of life formulas. These formulas are not necessary. However, they do cut out a lot of calculations in later mathematics. How late? Really late. Right? Let's say, I don't know, undergraduate level 300 or 400 courses. Definitely graduate school for Fourier series and stuff like that. But you might encounter the guys earlier if you go the math, like math major or electrical engineering or so on. So what is this? If function is odd, then integral from negative a to a of f of x dx is equal to 0. And if function is even, then integral negative a to a f of x dx is 2 times the integral 0 to a f of x dx. Now, for odd functions, the test was f of negative x equals negative f of x. And for even functions, test was f of negative x is equal to f of x. Functions could be odd, even, or neither. For instance, e to the x is neither. It's not even, it's not odd. X squared plus 3 is even. X cubed minus 70 is odd. So these are important things that you need to consider. So how does this help? Well, if you have an example, let's say you're calculating sine x dx from negative 2 pi to positive 2 pi. The answer is immediately 0 without calculating anything by the theorem above. And the reason for that is that the sine is odd function. And odd functions on the symmetric interval have the value of integral to be 0. We did this problem, similar problem, with the sine and got the 0 and then learned how to fix that if they are asking for area. But as far as computing integrals goes, as long as you have odd function on a symmetric interval, answer is 0. And we know that we do have a symmetric interval in case of this negative 2 pi and 2 pi. For even functions, let's say you have x to the 4th minus 3 from negative 5 to positive 5. Everything dx. So if you have this situation, you say, oh, well, that's even. And if it's even, that means that you can change the limits of integration from negative 5 to 5 to 0 to 5 and double the integral. Now, this is the reason why I call this quality of life. Right? You are saving on calculation steps. Imagine how much steps of calculation I skipped on the previous example. Right? Because I know it's an odd function, it's on a symmetric interval, odd function on a symmetric interval gives 0. Now, even function on a symmetric interval actually helps us calculate less because it's much easier to compute at 0 and double the result at the end than to compute with negative 5 everywhere. 0 is much easier in computation, right, than negative 5. So both of these formulas can be avoided. Right? You can use whatever methods you know from before. However, right, if you know them, you see that sine x gives a 0 and the one on the bottom. Now it's easier to deal with. So I have 2 times x to the 5 over 5 minus 3 computed from 0 to 5. And that's 2 times. And now 5 5 to the 5. No, 5 to the 4. 625. I'm supposed to say 3x. Minus 15. That's 612. 610, I mean. And then double it. Good. So as you can see, all we're doing with these problems is cutting out on calculations. We are not learning, some crucial theory over here. Now the next formula is the one that is needed, and this is called the average value of a function. So the average value of the function f is given as 1 divided by b minus a times the integral a to b f of x dx. So this is our average value. So the average value will be computing the line that's averages the function. So say you have something like that. Let's say this is a and this is b. Then the average value is going to be, let's say, somewhere there. So this is f of x, and this one over here is f bar. It's the average value. Okay. Now this average value is also going to be known as the mean value theorem for integrals. And the mean value theorem for integrals pretty much says the same. We are using the same average formula, and then we'll do the examples. So let f be continuous. On interval a, b. There exists a point C in AB such that f of C is equal to the average, which is equal to 1 over b minus c. In this case we do a. Integral a to b f of x dx. So there's this extra piece right now of information which tells you that the value c exists. Now where would that value of c be? As you can see, it's right there. That will be value of c. So there exists a point such that the average value and the integral are the same value. Just want to find, let's say, two examples, one easy and one like a function type of setting, like an applied problem. So let's work out some of the which problem should I work on? 21 through 28. Anyone? Just call a number like on bingo. 20. Someone said 23. I caught 23. I was eyeing 23, but then I wanted you guys to make that decision. And then you did. And the reason why I really wanted this one is what's the integral of this? Arctangent, very good. See? Alright, so the average value is equal to the integral from -1 to 1 of 1 over x squared plus 1 dx. So that gives us the inverse tangent, as you said, x from -1 to 1. And I hope you guys see. Alright, let's see what happens. This was even function, so we don't have to go from -1 to 1, but whatever. So we have the tangent inverse of 1 minus tangent inverse of -1. Now inverse tangent is odd function, which means that that minus sign from -1 can jump in front. So I have tangent inverse of 1, and minus gives me plus, and then I have another tangent inverse of 1, and this becomes 2 tangent inverse of 1. What's the tangent inverse of 1? Very good. So the entire answer is pi over 2. That's the average value of a function. Now, if I want to do the mean value theorem part for this, well, I have to equal the average to the function computed at that value c. So now the average is pi over 2. And the function on the other side is the original function when you plug in c. Some of you were very confused by this on the exam when we did the same thing for derivatives. You have a formula, and then if the formula calls for f of x, then it's x's. If formula is calling for f of c, then every x needs to be replaced by a c. So all I need to do now is to solve this. The fastest way would be to just flip both fractions and then subtract 1. So if I flip both fractions, I get 2 over pi is equal to c squared plus 1. Then I subtract 1. C squared is 2 over pi minus 1. And then I square root both sides. C is equal to plus minus square root of 2 over pi minus 1. And this is what we have. At these two values, you have the average to be equal to the area. So this was just, as I said, example to practice the skill. They give you some function, they give you the interval, and just say, do this thing. But clearly, we generally don't care about that. We care about the application that builds stuff so that we can further our technology and knowledge. So we look into, let's say, average height of an arch. The height of an arch above the ground is given by the function y equal 10 sine x from 0 to 10, no, to pi. So this is problem 33. What is the average height above the ground? So find the average height. Well, you have the height function, and you just go and say, all right, the average value of f is 1 over pi minus 0, integral 0 to pi of 10 sine x dx. Now you kick 10 out, becomes 10 over pi. Integral of sine x is negative cosine x, computed from 0 to pi. So we have 10 over pi, and now you have, what's cosine of pi? Negative 1. Okay, good. So that's going to be negative 1 minus, and now you have negative cosine of 0. That's another negative 1 there. And when you look at all of this, it's 2, so 20 over pi, or whatever units they had. Was it meter or feet? What was it? It's a lame problem, they don't even say. Whatever. Now, I don't know why would people look for the average height of an arch, but I would definitely look for the average height of a wave at sea. I have a ship, all right? And this is going to be the same calculation. See the sign goes a wave, no wave, a wave, no wave, a wave, no wave, right? So it's your sine function right there, with 10 over here being the amplitude of the wave. It's the height, 10 feet tall wave, right? And then the speed of the wave would go there. So if I have 10 feet tall wave, the sine of, I don't know, 30 feet per minute or whatever the speed of the wave is, right? I know stuff then, right? And I can, when we have those, that information, right, we can plug that into computer navigation and all of that kind of stuff. So it's very important to do these things. Now, clearly, software does this for us, but someone at one point had to program the software to do these things. And that's 5.4. So we start from 4.9, reviewing the basic integration, just the formulas for integrals. Moving into 5.2 for the definite integrals that are talking about the area under the curve. The blue formulas are again from 5.2, talking about the equations that we might use, the identities, right, for integrals. And now the new stuff for 5.4, between even and odd functions. So you have the definition what even and odd means. That was all the way back in pre-calc 1. And then you move to average value. Average value gives the mean value theorem, which is in red, and that's that. It's a very short section. It has only 4 formulas, where two of the formulas are actually the same. Mean value theorem and average are the same thing. And that's that. So let's restart for the new section.